Okay, so so last week we started a section called Dreamfell, the Dreamfell morphism. So we did not yet define what is the Dreamfell morphism. We will do that now. So what we did in this section last week is that, so we proved this equality, which corresponds to that. This equal this. So you take a braiding like that. Give this braiding and you do like that and like that, and you get that. Okay, so using this lemma, we will be able to prove something about the dual of the braiding morphism. And then after that, we will define the Dreamfell morphism and prove a result about it. So let x star y star be left dual of x and y in C braided monoidal category. Then the dual of the braiding morphism is the braiding of the left dual of the object. Okay. And the proof will be, so yeah, the proof, in fact, will directly use what we did in the previous lemma. So proof so Cxy star is equal to xy as a braiding. And then remember that the dual of a morphism is pictorially like that. Okay. Then you just need to apply 2 times the previous lemma. So 1 time. So you apply it here. So up to here. Is equal to lemma so like that. Y star x okay. And again, so we apply the previous lemma again. Again. Previous lemma. And you get okay. So in fact, the first you use you use this way, and then you use the other way, I guess. Because you see, you have one. This left string is above, so you apply the first one here and the second one here, because here the left string is above and here it's below, so it corresponds to the second, this one, and this correspond to the other. So it's okay. It's immediate. You apply 2 times. It's okay. Okay. Then let me define what is called the Dreamfell morphism. So it's a natural transformation between the identity functor of the category C and the double dual functor. So let the Dreamfell morphism so here the sense of natural transformation. IDC to the double dual. So I guess we should take C to be a braided a braided rigid monoidal category. Let's see, be a braided rigid monoidal category. I guess we need here. We don't assume rigid. We just assume X and Y have a left dual. But here, if you want a Dreamfell morphism, if you want this functor, you need to have a at least we should assume it to be left rigid, but anyway, rigid. So the Dreamfell morphism is a natural transformation between the identity and the double dual functor, defined as follows. Defined by the following composition, and we will see the picture of that after. So it's a natural transformation, so it's defined as a family of morphism. So you start from X, you apply IDX tensor co-evaluation of X star. You get X tensor X star tensor X double star. Then you apply the braiding XX star and identity X double star. You get star tensor x double star, and finally you apply the evaluation map of x tensor id x double star, you get x double star. So the picture for that is as follows. So you start from x and you apply the co-evaluation map of x star. Then you have the braiding identity, and then evaluation of x identity. Okay, so you have something like that. And in fact, we will use this pictorial representation to prove the following proposition. Ux tensor uy equal ux tensor y composed c x yx composed c x y. And so we will prove that. So in particular, so let me write here. Which color? This color. Remark by the next position. So what? U is tensor as a tensor structure. As a tensor structure. If and if C is symmetric. Mean CYX tensor CXY equal identity of X tensor. So okay. So a tensor structure mean this equal this. So U is a natural transformation. Okay. So wait. Yeah, okay. Substructure. Okay. Okay. So proof of that. The proof will be completely pictorial. So ux tensor uy equal like that. X. And remember, making the tensor pictorially is just putting in parallel like that. It's when you put two things together like that, which mean tensor. So this is equal to. So you can make it. You can move. In fact, you can. So you do like that. Y. The point is to put this picture in the relevant way to understand what kind of manipulation we can do. So here we did nothing. We just move this one a bit like there, and then we will move this here. So all these manipulations are allowed. They correspond to the axiom, I guess. So when you put that here, you get something like that. X, Y. Okay. And okay. And here you can see it directly as so this one is coev x tensor. I will write it directly. Coev coevaluation map of x tensor y star. So we did almost nothing. Just move that here and that here. So we are up to isotopy. This is the same picture. Now we will start to make some non-trivial manipulation. So we will use the naturality. So I guess we already did that before. Yeah. We will use a kind of naturality we used in this proof. Remember, we moved this equal this. So you have this, you can move this kind of picture. So we will do almost the same here. We can move, we'll use a naturality to move that here. So you will see what I mean. exactly as we did before. What I saw. Naturality. What picture do we get here? X, Y. So I have no room. So X, Y. Okay. So this one is okay. And yeah. So so how I am doing what I'm doing. So you move like that, and then you again. So let me draw it. Let me take more step. So you have that here. Move that, and then that. Okay. Okay. So you see what we did? I missed something, maybe? No, oh, it's okay. And this one I need to put it, because I will do it again. I want to do like that. So see what we did? We just put it here. So we can do that by naturality exactly for the same reason what we did here. So the idea is that you can put a morphism, can move it, can cross the braiding like that, and you use a unit which don't appear. So you have that, okay, and you do it again. Here you will put it inside. So let me do, because he will go below. So I will do like that. Okay. And here you will also go below, if I'm not mistaken. So you will go below. So again by naturality. So X, Y, the co-evaluation map. Okay. That. So here is the same. So you see. Okay. So in fact here I also use the hexagon, but maybe it's not necessary. Anyway, so let me think. So you have that. Okay. And then what we want to do is to move. So let me check. So here we apply the naturality we said. So we'll do like that. And you put this one below. Okay. So we just move this here by naturality below. Okay. Now we just need to apply the hexagon relation here and here. So we just need to decompose this braiding. Okay. So we will apply the hexagon 2 times. Hexagon axiom 2 times. So okay. So we get x, y, so co-evaluation map. And then you have this one. And like that. Like that. Okay. So we did the first. Then we have to put this one. Okay. And then we apply the again the hexagon. So so what it is? Okay. So I missed something or not? So this one. Okay. Okay, here. So here. Here. Okay, and then evaluation map. Evaluation map. Okay. So it's okay. So this is the first decomposition and the second decomposition. And the one here. Okay, then then you just need to apply 2 times the Young-Baxter relation. So the Young-Baxter relation. In fact, the point is that we want to make what we want here is that to appear. So we want something like that to appear. So we will use the Young-Baxter relation several times here to make this thing appear here. So So we can apply it first here. So that will make one breeding here. And then we will apply it a second time. Okay. So we will apply the Young-Baxter relation here. Young-Baxter relation. And so we get x, y, and then we will apply it 3 times. Wow. Okay, so let me go quickly without doing mistake. So then this one and this one. Okay, then you have that. That. 1, 2, 3 here. And the evaluation map. Okay, so now we will apply the Young-Baxter relation. So this one is for the. So I will change the color to avoid any confusion. We'll apply the Young-Baxter relation here. Let me put 1, 2, 3. No, not here. Okay. Not here, not yet here. Here. So it's equal to Young-Baxter, pink. So x, y. The correlation. And what you see? Okay, so the beginning is the same. So, yeah. Okay. Now, this one. And this one. Whoa. This one. Okay. Okay. So we just apply it here. So let me check whether I did not. Yeah, it's okay. Okay, so now we can apply it again here. We take the green. And we will be almost done. We make appear like that this term by this manipulation. So last Yang-Baxter. So now we have the term we wanted. Like that. Like that. The correlation. Okay. And then so this one and this one. Yeah. Okay. And this one. Oh. Okay. And finally, so you see, yeah. Now it just remains to apply the hexagon relation back. So here, 1, 2, 3, 4. So we can apply it. Here we have the decomposition. This is a decomposition of that. Like that. So this one. So we can draw, we can apply the hexagon relation back to get. Okay, so we apply it here. It's equal to hexagon so we still have the double braiding. And now you have that, as I said. Okay, and like that. So you see this decompose like that. This is exactly the hexagon relation. No problem. Okay. And you see that this is exactly the Dreamfell morphism for X tensor Y. This part. And you have the double braiding as expected. CYX compose CXY. Okay. So this is a so for people who are already know, who are comfortable with manipulation with braided category, this proof is straightforward. But for people who discover this theory, it's a good proof where you can see a lot of manipulation. So it's a good way to well digest what kind of manipulation you can do in this framework. So it's really, really a good proof. Useful to understand what kind of thing you can do in this framework. Okay. And this is what I am mainly interested in this course, to understand the mechanism of this categorical framework. So in the rest of this section in the book, they use the Dreamfell morphism to prove some result or reprove some result due to Radford and Larson about the antipode. Yeah. So, but I will skip the details. Antipode of algebra. So the rest of the section is dedicated to use the Dreamfell morphism to recover the following result. So we skip the details. So by that I mean we skip the proof. So first result, corollary by Radford, due to Radford first. The antipode of a finite dimensional of algebra has orders dividing 4 dimension X. The antipode. We already mentioned the force, something called the force dual Radford theorem. And then we get that the antipode in that case should be of finite order. And in fact, we can have a better statement about the order of that. The finite dimensional of algebra H has when people the finite dimension of as order dividing for dimension of H. Remark. In all known example, it divides to dimension H. but is open in general. We don't know if it is true in general. Okay, so let me make the pause. Pause. Okay. So this Radford theorem can be proved using the Dreamfell morphism. I will not explain the details. And this other result, due to Larson, Radford. So I don't know if the use of Dreamfell morphism recovers the proof of this result, or if this result was originally proved using the Dreamfell morphism. I don't think so, but I'm not sure. Semi-simple off algebra over. So this is very, very famous theorem, one of the most famous theorem in off algebra theory. A semi-simple off algebra over a field of characteristic 0 is co-semi-simple. So there is not even finite dimensionality here. So a co-semi-simple off algebra H over a field K of characteristic 0 is co-semi-simple. Okay. Yeah. So I skip the details of that. As I said, I don't want to focus too much on off algebra in this course. So as you know, there is a course of Yilong Wang in this same semester than me, who is focusing on off algebra. So, new section, ribbon monoidal category. Okay. So what's a ribbon monoidal category? A ribbon monoidal category is a monoidal category with a ribbon structure, and a ribbon structure is a twist with an additional property, with an additional yeah. So what's a twist? A twist also called balancing. Ça marche le son, hein? Le son, ça marche? Ah. Balancing transformation. On a braided rigid monoidal category, C. So is an element theta. There is a natural isomorphism between the identity functor to itself, such that it's yeah, in fact, he has the same. He has almost a tensor structure as for the Dreamfell morphism. He has a tensor structure up to putting a double braiding like that. And in fact, we will see that we can provide a twist and then a ribbon structure using the Dreamfell morphism. We will mention that for the Dreamfell center of the category of representation of the finite group. Okay, so this is a twist, and the twist is called a ribbon structure. If you have that twist of X dual is the twist of X dual. Okay, and finally, a ribbon category is a braided rigid monodial category equipped with a ribbon structure. So finally, a ribbon category is a braided rigid monoidal category. Is braided rigid monoidal category equipped with a ribbon structure. With a ribbon structure. So in fact, this notion of ribbon structure, so we will see in the next example why it's called ribbon, but in fact, we can mention here that in the case of a fusion category, I don't know what if it is true in general, but in the case of a fusion category, for a braided fusion category is ribbon if and only if it is spherical. So the notion of ribbon structure, the existence of a ribbon structure is equivalent to the existence of a spherical structure. So this notion of ribbon structure at the level of fusion category is not essentially new. It's maybe one of the goals of this section to prove that in the fusion category case, it's the same thing as spherical structure. But this ribbon, so this way, as I will explain, is related to the topological ribbon, and it is used by Reshetykhin and Toureyev to make invariant of link, which recovers Jones polynomial. So it's very interesting, this approach. So we will see later that a braided fusion category is ribbon if and only if it is spherical. So what about the general case? I don't know. I don't know if it is you have counterexample in general case or it is open in general case. Maybe it's written somewhere in the book I did not found yet. So, exercise. So, the expected example of ribbon structure using Dreamfell morphism. So show that the Dreamfell morphism U is a ribbon structure on the category rep Dreamfell double of finite group, which is the same as the Dreamfell center of rep of G. G finite group. Okay. So I don't know if so according to this exercise, the double dual functor in this category should be identity, because it assumed to be a ribbon structure, so it's an automorphism of the identity functor, but it is defined as a natural transformation between identity and double dual. So the double dual should be identity here, and I wonder whether the Dreamfell center is a ribbon on every braided tensor category where the double dual is identity. I guess not. It will be too strong, but I don't. Okay. So now the universal example of a ribbon category, which explain the terminology ribbon. So the following example justify the term ribbon, and in fact, it will be. We will explain it is universal. We'll mention that it is universal. The universal ribbon category in some sense. So recall the braided monoidal category of tangle it generalized as the category of frame tangle where the string are replaced by oriented ribbon. So I will draw some pictures to explain what I mean. So it generalized as the category FT of framed tangle where strings are replaced by oriented ribbon. Strings open or open or close are replaced by oriented ribbons. Okay. So by string, you can have something like that or something like that, an open or a closed string. And it is replaced by oriented ribbon. So it can be like that, or it can be like that. So this is an orientation. And so you have like something like that. And so I don't know if you need to orientate the closed ribbon. It is necessary or not. I'm not sure. I'm not sure whether we need to orientate the closed ribbon. But so maybe no need to orientate the closed ribbon. I don't know. Because in fact, the orientation, so the point of the orientation here is that the composition of the morphism. So remember that the tangle or frame tangle, the object are natural numbers, and the morphism are the tangle. So you can compose the morphism and by gluing together this tangle. And the gluing should preserve the orientation. So if you have a closed string, then there is no composition, so there is no point. Maybe you don't need orientation here, I don't know. Anyway, so this, as I said, the composition should preserve the orientation. And the composition is given by gluing together. So which have to be glued together preserving the orientation. Preserving the orientation. Okay. So I mean, so you have that. And you will compose like that. So this is that is okay. But not okay. This is not okay. You cannot do that. Not okay. Okay. Now, so this is supposed to be a ribbon category. So we need a twist. And in fact, the twist is given by the topological twist of the ribbon. In fact, you twist it 2 times. So you make 2 times the topological twist of the ribbon. So there is a twist in the category FT given by the double twist of ribbon. By the double twist of ribbon. As follow. Equal to, so you have the object X, So here natural, not natural number. Anyway, you remember that in the tangle, the object, you do something like that, and you have the tangle in the middle. So here it's like here, the object here is like you can take 1, the natural number 1, if you like. So oriented like that, for example, and then you make the double twist. So this is not easy to draw. Double twist of the ribbon. So this is just the topological twist of a ribbon. And by this, this means the other, this shadow mean you look the other side of the ribbon. So you twist it 2 times like that. That provide so there is a twist providing a ribbon structure on FT. Okay. So what about the so first, is it really a twist? So it is a twist thanks by the following picture. Pictorial proof. Pictorial proof. So you start from. So this is really not easy to draw. So in fact, you start from 2 x tensor y. So you have 2 ribbon like that. 1 for x, 1 for y, and you make the twist of these 2 ribbon. So it's quite. Let me try to draw that. Okay, it's not easy. That oh. Yeah. So here you have the shadow part. One time. And the second time. I hope it's clear enough. But in fact, you have just you take 2 band of papers, 2 ribbon of papers, and you make the physical twist of two ribbons of paper, you see, you get something like that. So the twist saying that this is just up to isotopy. So I put the orientation. I'm not very comfortable with this notion of orientation here. Yeah, I will explain. So you see, we are twisting. So we do a double braiding of the ribbon, and we are inside twisting the ribbon. So in fact, this decomposes as follows. Up to isotopy, you are just as you are just making the double braiding. And then you are twisting the double twist. So you can move, topologically, you can move the inside double twist here, and this one also here directly. So this is just what you get is exactly that. As expected. CYX, CXY. So that's okay. And it's ribbon. And then for the ribbon, so it's not explained in the book. So I did not get too much time, but for the ribbon, I have a problem with orientation. So let me check. So if you to get the ribbon structure, you need that. So by picture, if you have that, this is so like that. Okay. So you have the orientation like that, and then it's take the dual. So you apply evaluation and co-evaluation map. So here they are drawn as a ribbon. So you have something like that. And okay. So topologically, what you get is that. So this here, I have a problem with orientation. That's why I need to better understand this point. So I have a, I would put a question mark. I have a doubt here. Is it equal to that? I don't understand. Because you see, when you apply you have this map, you apply the dual, you are doing like that, and so the orientation is there. So it's supposed to be there. So what you get here is not really, in fact, you have two twists. You can, in some sense, you have plus or minus according to whether it's like that or like that, I don't know. So when you make the dual of that, if this is plus, what you get is minus, I don't know. So I put a lot of question mark here. So this question mark means this need to be clarified. This last point need to be clarified. So it's not written in the book. Maybe they will have more details in the paper by Nikshych and Toureyev. But anyway, you don't need to take too much time about this example. If you're interested, you should check this reference. Check paper by Nikshych, Toureyev. So they wrote, I guess they wrote several papers. Nikshych, Toureyev. And this paper is called ribbon graph derived from, so let me check, name, ribbon graph and their invariant derived from quantum group. The paper written in published in this time where you have ribbon in the title, so you can find it. Okay. Okay. Now. So as I said, this frame tangle category is a universal ribbon category in the following sense. So moreover, Ft is the universal ribbon category in the sense that for all ribbon tensor category C and for all object X in C, there is the unique natural in some sense functor F from the frame tangle category to C, sending the generating object of Ft, the generating object so remember, the object in the tangle category are natural number. And so the generating object and the tensor structure is given by addition. The generating object is the number one, natural number one. Generating object of Ft to X, preserving the ribbon structure. So there is a unique natural, in some sense, functor from FT to C, mapping the generating object, so 1, to the chosen object X, preserving the Riemann structure. So in that sense, it is universal Riemann category. It is a universal as a Riemann category. Okay. So let me explain what I mentioned about the invariant of link. Remark. So the home space so the morphism between 1 and 1 in this category is it's not the home space, I guess it's home set. There is no space, it's not a linear category. Is the isotopy. So this set is the isotopy classes of framed link. So link made with ribbon is isotopy classes of framed link. So for example, you can consider this one. If I am not mistaken, a framed link is a link made by ribbon. Ah. See? Example. Framed link. So you have this frame link. And in fact, you will use the functor f to make invariant of frame link. And above functor f define an invariant of frame link. An invariant of frame link L with value in N1K. So remember, N1C, sorry. Remember that we C was taken tensor. So this is just a scalar. Call that C is tensor. Okay. So this invariant is denoted like that. Restricting to IF, depending on the category C and the chosen object of the link, called the Rishitikin to IF invariant. So we are here in the domain of topological quantum field theory. So it's so it's close to what is called topological quantum field theory. Rishitikin. In fact, Rishitikin topological quantum field theory is to make invariant of manifold by using triangulation, and you choose some category, and in the triangulation of a manifold, I don't remember, the vertex and the edge correspond to morphism and object, etc. And then it is closed. You get a scalar which is an invariant of the manifold. So this is the philosophy of the topological quantum field theory developed by these two guys, which is taking to IF invariant of L. In particular, for example, if C is the category of representation of this quantum deformation of SL2, and you take X to be the standard, the usual two-dimensional representation, irreducible representation, then what you get is the Jones polynomial. Then RTCX is essentially, so I did not check what they mean by essentially here, the Jones polynomial. This is very important because, as you should know, von Jones got the field middle for his Jones polynomial. In fact, he started from analysis from subfactor theory to make this invariant of knot and link. But according to that, it can be recovered in the categorical framework. Okay. So let me end this by a naive question. In fact, when I prepare this note, I ask myself, what's the point of considering a framed link and ribbon category to make such invariant? In fact, you should be able to make the same thing just by the braided category or the tangle, not the category of frame tangle, but just tangle. I don't. What about just? There may be an explanation, but I don't know. Just on T1 isotopic classes of usual link. By what about, I mean, we may, so if you have this functor as above, not from the frame tangle category, but from the tangle category, we may get invariant of link in that. So I put a lot of questions now because it's not just a naive question. I don't understand the point of taking ribbon here. Can we cover transpose? We need to better understand why we need the ribbon to do that. So, okay. So we will stop here. So next session will be next week on Monday, and it will be the last session of the semester. Okay, so see you next week.